Okay, looking at the Chapter 19 Electric Potential and Energy worksheet. Once again, I only put one problem here, but it's got many parts. We have two parallel plates having surface area of 0.0400 meters squared each and a separation of 2.50 millimeters. So once again, just starting right off the bat, I'm going to draw so this has area equals 0.0400 meters squared and separation of D equals 2.50 millimeters. So there's my picture, and this has a voltage difference of 10 volts. So I'm just going to go ahead and arbitrarily say that this one is at 0 volts and this one's at plus 10 volts. That's a voltage difference of 10 volts. Answer the following questions based on this configuration, assuming air. The electric field between plates. Well, it's difficult, but it turns out that this is a straightforward problem. The electric field between the plates has a magnitude equal to the voltage difference divided by the separation. That's it. Now, this is only if you have a uniform electric field, but between those plates, as we talked about in class, you do have a uniform electric field. And so that's just going to be 10 volts divided by 2.50 times 10 to the minus third meters. So that's equal to, and again, 2.5, that's basically a quarter with offset. And so the answer you get here is 4,000 newtons per coulomb. Now notice, it's a volt per meter. 4,000 volts per meter is the same as 4,000 newtons per coulomb because a volt per meter, volts are joules per coulomb, so it's a joule per coulomb per meter, but a joule is a Newton meter. So a volt per meter is a Newton meter per coulomb meter. Well, cancel those meters, and you have Newton per coulomb. So that's the electric field. Now, what direction does electric field go? It always goes out of positive into negative. So the electric field in here is going like that. Now, I arbitrarily chose the right side to be positive, the left side to be 0. I could have chosen one to be positive 5 volts and one to be negative 5 volts. There's lots of different options for what I could have put there. What was key was the voltage difference was 10 volts. And the electric field lines are going to go from the more positive to the less positive plate. So, number one, the answer was 4,000 newtons per coulomb. Number two, what's the capacitance of this item? You might notice that in the earlier version I had B and C reversed. And looking at it, I was, well, duh, you want to do the capacitance first. This is a physical capacitor which has the simple equation of capacitance is equal to kappa epsilon 0, permittivity of free space epsilon 0, times the area of the plates times divided by the separation of the plates. So if it's air, kappa is just going to be 1.00. Epsilon 0 is 8.85. And I actually looked it up to way too many decimal places. Just to get us a couple more, 8.8542 times 10 to the minus 12. And the units are coulomb squared per Newton meter squared. And then times my area, which was 0.0400 meters squared, divided by my separation, which was 2.550 times 10 to the minus 3 meters. Looking at the units, we're going to see that the meters squared here cancel, and I'm left with coulomb squared per Newton meter. So I have this is equal to 1.42 times 10 to the minus 10 coulombs squared per Newton meter, or as we prefer to write, 0.142 nanofarads. Now we have what's the charge stored on each plate. I'm going to write this one just right here. We have the relationship Q is equal to VC. Remember, that's the way I memorize it because it's the shopping place. So that's going to be 10 volts times 0.142 nanofarads, which is going to give me 10 times 0.142 is 1.42 nanocoulombs. That's 4. Now the energy stored. These are not long. You notice these equations are short, but of course you have to understand how they work. So the energy stored in a capacitor, remember a capacitor stores energy in the form of electric field or in the form of a charge separation. And that energy stored, which we usually use a U for, a capital U by the way, is equal to 1/2 CV squared. So that would be 1/2 of 0.142 times 10 to the minus 10 farads times 10 volts squared. So that's going to be 14.2 nanojoules. Or 40.2 times, oh wait, I forgot to divide by 2. 14.2 divided by 2 would be 7.1, right? I have 3 significant digits here, though, so 7.1 isn't going to cut the mustard. It's 7.08 nanojoules. That's a 9. Okay, if an electron is placed at the negative plate, so in this case, I didn't put any negative plate. You're like, well, what do? The more negative plate, so the one with 0 volts in this case, what will its kinetic energy be when it hits the positive plate? So I'm going to have an electron. So let's just put an electron in there. Here's an electron. It has a charge Q equals minus E. Minus because it's negative. So the electron is in the electric field. The force is QE. Since E is going to the left in my picture and Q is negative, that means the force is to the right. So it's going to have a force that accelerates it across those plates. We could calculate the acceleration, but I didn't ask you to. I'll actually do that. The force on the electron is equal to QE is equal to minus 1.602 times 10 to the minus 19 coulombs. Excuse me. And the electric field of 4,000 newtons per coulomb. So if I just take and multiply those, which I did not do beforehand, I didn't think to do that. So that's 6.408 times 10 to the minus 16 newtons. And you're thinking, well, that's a really small force. But according to Newton's second law, sum of the force is equal to mass times acceleration. So the acceleration is equal to the sum of the forces over mass. Assuming that's the only force, that's going to be 6.408 times 10 to the minus 16 divided by, what's the mass of an electron? Well, the mass of an electron is small, divided by 9.109 times 10 to the minus 31 kilograms. And so that gives you 7.03 times 10 to the 14 meters per second squared. And as Doc Brown would say, Scott, that is a very large acceleration. That electron is going to be accelerating like crazy. And so what we're going to calculate here, just coming back to the problem, if the electron is placed in the negative plate and released, what will its kinetic energy be when it hits the positive plate? Well, we know that it had this potential energy stored, but what we want to do is say how much energy is going to be transferred to that electron. So we know that delta V is defined as the change in potential energy over charge. So the change in potential energy must be Q times delta V. So that would be 1 electron charge. It's going to be minus because it's a negative charge. I'll just put E without a minus sign there. Maybe. Times the voltage difference of 10 volts. Notice it doesn't matter what the capacitance is. It doesn't matter what the separation is. It doesn't matter what the electric field is. It matters what the voltage difference is. If it's a 10 volt difference and I have an electron going through it, it's going to have a change in potential energy of minus 10 E times V. Electron charge times a volt. Or converting that into joules, that would be minus 1.602 times 10 to the minus 18 joules. So if the potential energy is going to drop by 1.602 joules, how is that going to help me answer? Well, this is a conservative system. There's no air resistance, no friction here that we have been told about. And so our energy is constant. So delta E equals 0 is equal to change in kinetic energy plus change in potential energy. So change in kinetic energy must be equal to minus the change in potential energy. So the change in kinetic energy is going to be plus 1.602 times 10 to the minus 18 joules. So if it starts at rest, so it says it's placed and released. That implies that it starts at rest. So its kinetic energy when it hits the positive plate will be 1.602 times 10 to the minus 18 electron volts, or easier to write, or excuse me, 1.602 times 10 to the minus 18 joules, or easier to write, 10 electron volts. And then its final speed from part E. Now we saw it has incredible acceleration, so we're going to expect it to go pretty fast. How do I calculate that? I'll do it using kinetic energy. I know that kinetic energy initial equals 0. So kinetic energy final is equal to change in kinetic energy equals 1/2 mass times speed final squared. So the final speed squared is equal to 2 kinetic energy final over mass. So if I square root both sides, I'll have V final is equal to the square root of 2 kinetic energy final over mass. And then I just put in my numbers. So that's the square root of 2 times 1.602 times 10 to the minus 18 joules divided by 9.109 times 10 to the minus 31 kilograms. And that gives me a speed of, oh my goodness, of 1,875 and I'm just going to, because I have 3 significant digits, I'm just going to put 1,880. That wasn't 1,000, by the way. That was 1, 2, 3. That was million. That's going fast. 1.88 million meters per second. So you can see that it does not take much voltage to make an electron go very, very fast. This is not a relativistic speed yet. But if you go through 100 volts, you are starting to reach the relativistic regime for speeds. Okay, moving on. If the air between the plates is replaced with a dielectric with kappa equals 3, and the voltage difference between the plates is maintained at 10 volts, what is the new charge? Now let's go back. Capacitance, if you look here, capacitance is kappa times epsilon 0 times A over D. Epsilon 0, the permittivity of free space, that basically tells you how easily you can pass charge through free space. Kappa is going to give us the correction for any other material. So if kappa is equal to 3, then it's going to be 3 times harder to pass charge through the free space, or through the space, because it's not a free space anymore. So that means my capacitance will be 3 times bigger. And if my capacitance is 3 times bigger, then since Q is equal to VC, my charge will be 3 times bigger. So all I really have to do is take this Q is equal to VC, C is equal to 3V, so it's going to be 10 volts times 0.142 nanofarads. 3 times 1.42 nanocoulombs gives me 4.25. Interesting that I have, yeah, there we go. I have 2 different things there. Nanocoulombs is the charge I will have on the plate in this case. Finally, draw the electric field lines between the plates and the equipotential lines at 2-volt intervals. So I will start by drawing my parallel plates in black. And so I'm going to actually move over here to free space and make it big. Here's my parallel plates. And so I put this side at plus 10 volts, this side at 0 volts, and then electric field lines. As I said, the electric field lines are going to be uniform inside the capacitor. The spacing for these should be exactly the same for each line, and the line should be exactly straight. And then I need to find the equipotential lines. Equipotential lines are by definition always perpendicular to the electric field lines, because those are the lines on which there is no work done if a charge moves. There's work done if the charge moves parallel or anti-parallel to the force. So they have to be perpendicular. And because this is uniform, the energy is changing linearly with position. So for instance, here in the middle would be 5 volts. Well, I was asked to do 2s, so that means I would have like, here's 4, here's 2, here's 6, here's 8. And so now these lines should all be equally spaced. I tried to equally space them, but this is artistic license. Every line here is straight. Got it? So these are my equipotential lines in blue. 2-volt line, 4-volt line, 6-volt line, and 8-volt line. So there you have it. And we finished the problem.